Oh.
So last technique to prove that some problem is in FET. Well, we will use actually a special parameter. It's called tree width, and it allows to use dynamic programming on almost every problem in NP. So it's really powerful technique. So the parameter will be the tree width, and our first task is to say what is this definition. So unfortunately, we have to go to some abstract definition. So what is the idea? We receive a graph, something like this, for example. And okay, what is happening? Sometimes a graph is almost like a tree. So I did some routing project, and something like this happens, and maybe something like this, and so the structure, and then here is some block, and here is some block, and the graph looks almost like a tree, except if we are allowed to like somehow contract the nodes. And why is this interesting? Think about the vertex cover problem. When you do it on a tree, it becomes very easy because greedy algorithm succeeds. So we call vertex cover problem if the graph is a tree. So let's even say a rooted tree. So why greedy algorithm works? So
Greedy means we take
greedy is
What
that
are we trying to solve?
vertex cover problem.
Okay.
Yeah. So we just look at the edge, starting from a leaf. Let's look at neighbor from edge. So will we put this in the vertex cover? Leaf has degree 1 node. We will never do it.
Yeah.
So we will put this in the vertex cover. And then it means we can remove this node, and we are in the same problem again.
We can remove the whole subtree.
Yeah. So vertex cover on the tree is really easy. So
Why don't we begin from the root?
Because we cannot just
I see.
remove
Yeah.
subtrees. We need to begin from
Yeah,
the
yeah,
lowest
okay,
level,
Okay.
Yeah.
and then just.
But then the idea is, what if graph is almost a tree? What can we do in this case? And this is the whole idea of this tree width. Obstacle is that definition of tree decomposition is difficult. So I need to explain this. And then if you remember out the dynamic programming we trained at last lecture, everything is clear how to solve tree colorability or vertex cover if this tree width is small. So what I'm saying here is that, like, look, if we can like merge some of the nodes, we could like turn this into some acyclic part, and we can do the same in the graph here, and maybe we end up with a tree. So then there are two questions: how do we merge the node, and then how do we run dynamic programming? A second question is hopefully easy. So how do we get a tree? And so a tree, so given a graph, tree decomposition is a tree consisting of bags of nodes that we somehow contract. And there are two rules for valid tree decomposition. So for every edge, we need to have a bag that contains both endpoints of the edge. So here EF is an edge. Let's look at this edge. And there should be a bank here. Okay, I didn't write it carefully. EF, let me check on the example. So I'm stealing some slides from Max Planck Institute. I mean, there are many courses. This is a course that exists already very long, because so I found 3 years ago. And then there were fewer courses on parameterized complexity. I will put a link on the wiki to this course. I think they have nice slides. It's easy to read the slides. Okay, so here this edge appears in this bag. So that's the first condition, and then you can check for each edge. GH is there, CD, and so on. Where is CD? I don't see it. On the top. Okay. And second condition is that if we fix one node in the graph, for example G, then we look to all the bags that contain the node G. They must be a connected subtree. So again, if we look, for example, to the node C, so what are the nodes that contain C? It's here, only two, and the third one. Again, a connected tree.
How do we construct the bag? It's not that obvious.
Yeah, So this is a big question. Okay, let me finish one more definition. So what is the tree width? It will be the important parameter for our parameterized problem. It is the max size of a bag minus 1. Okay, now your question, how do we construct the tree? So there is an algorithm that runs in time order w cube times n to the power of 1 by Botlander from 1996. So it's very slow algorithm, but our goal is to prove that the problem is an FPT. Then there is a 5 approximation algorithm that runs in time 2 to the power order w times number of nodes. So it gives you a tree that may be 5 times bigger than the optimal tree after binary search. So, but it runs in time linear and n in the graph. So this is exact 5 approximation, and then there is a w, an algorithm that runs in polynomial time that gives you a tree of width at most. So if the best tree has width w, then this it produces a tree of width w times log w. So that's for your question, how to compute. All these algorithms are complicated. So there's some deep mathematical research behind them. I haven't studied any of them yet. Okay, so now where is? Okay, let's do some examples. Let's present the graph. So if you're given a cycle, oh no, it's difficult. Now I will teach you a second definition, which is easy to understand, and then we will do some examples. There are many equivalent definitions. The example is a game. So there are 2 players, the police and some criminal. And yeah, so there are W police guys. And police, they have, each police guy has a helicopter. It can fly somewhere. And there is one criminal who runs around in the graph. It can go to neighboring nodes. And the goal is that the police wants to capture the criminal. That means that police wants to land on the criminal. Criminal can, so the police is on nodes in the graph. So the W police guys, each police guy can stand on the node in the graph. And then for a criminal cannot move beyond this node. For example, if there is a police here and a police here, then the criminal can move freely in this graph, but he cannot cross a police guy. So he can only move to one of these 3 nodes, because here he has to step on the police and he will put him into prison. And the police can also move. For example, if there are 3 of them, then a police here can go in the helicopter, it goes up, and then can land here, for example.
Okay.
And so if the criminal is here, it's good news because the police can capture the criminal. Like if this guy is here, then this police can go in the helicopter and fly here, for example. Now when the thief sees that the police is landing, he can run away, but he can only run away here. Now there is a bit of a problem the police has, because if this guy goes into the helicopter, so he disappears from some time, and he wants to land here, but the thief can escape. So I gave a bad move.
No, but we can just move the right guy to the. We'll move H to the G and then D to the H.
Yeah, this was a
It's
problem.
checkmate.
So when I move this here, he should not land here, but he should land here. And then the thief can only stay here. So this is gone. And then the thief can. So this is the game. And so what is the tree width? So it's the minimal number of police that are needed to capture the thief. So so the thief goes first, he chooses a node in the graph, and then the police can move with the helicopters to the nodes of their choice, and they have to capture the thief. And so minimal number of police to have a winning strategy minus 1 is the tree width. So here I think it's easy to believe that 2 police will not work, because when the police is in the air, the thief can always move around. So if we drop this edge, all edges are all nodes are connected by 2 paths. So the tree width is exactly 3. Well, I think it's. Well, we know there that the tree width is 2. So with 3 police we can win. With 2 we cannot win. Okay. So then some questions, like tree width of a tree. If the graph is a tree itself, then it will be 2 police will be enough.
If a graph is a tree, 2. If a graph is a simple path, then one guy is...
Yeah, so we just move it towards a leaf. Like we make the subtree smaller, we pick some subtree and we make it smaller, and with 2 police they can move. But also, what would be if we start with the tree here, imagine we start here with the tree, what would be the tree decomposition here?
If we start
It's just all the edges.
Yeah. So
just one with one.
Yeah. We built the same tree here, but like the dual of the graph or something. How is it called? That edges become nodes and vice versa. Or the corner. Okay. So for tree it's with 1. For cycle, what is the tree width of a cycle? 2. For the police, it's kind of with 3 police.
Stand on the diameter.
And then the police moves in the direction of the thief. Next one, for the grid graph. So let me draw a grid graph.
Well, it's the first time I have encountered game theory definition that is actually easier than
the original definition. I know the feeling. So a grid graph. So let's say n by n grid. So what is the... So it's clear what is grid, right?
Yes.
Just so if we have n by n here, what will be the tree width?
We can immediately capture with 4.
4? I don't know how you do this.
If a thief chooses any node to land on, then 4 policemen. We need to land straight on here.
So n is probably enough.
The
But
tree
we
width
have
is...
a diagonal. No?
I think n plus 1 or n plus 2. So let us think. So the thief goes here or something, and then we can put police like here, and we need 1 more police that's in the air. So now the thief cannot go to the bottom part.
Why do we put them in the line? We can put them around the thief, and then the one that's in the air lands on the thief.
Well, the thief moves first, so he goes anywhere, and then the thief can move any number of moves through he can follow any number of edges.
So he has as many moves as he wants.
It's not one step. Sorry, he can just.
And the police guys are the police guys are landed, and then the thief moves, or the thief moves first and then we land.
So the police guy must say where he wants to land. So the thief sees where the police guy sees the helicopter arrive, and he can run wherever he wants. But he cannot cross a police guy.
No. First we're given a graph. Then the police guys select which nodes to land on. And then the thief guy selects which node to land on and makes his moves. Right. And then after he has finished, the police guys make their moves like they can only move one edge at a time. Each of the police guys, right?
The police can move anywhere. This helicopter.
Yeah, no,
he
but-
can move
but-
anywhere he wants.
But one transition at a time.
Yeah, but
Uh-huh.
one police guy moves at a time, and the thief sees where this guy is moving.
One guy, one transition. Okay.
Mm.
Yes. So in this situation, what do we
Plus
need?
one, yes.
With n+1, we can definitely do this.
Okay, so
We,
yeah,
ju- we just cut the part.
yeah, you're right. So n+1 is optimal, but with n we cannot do it because when we make a cut in the graph, then when one police goes in the air,
Mhm.
the thief can always go through.
Mhm.
So he can always go to the largest half of the cut. So yeah, for grid it's n+1. Okay, that's already one exercise solved. What do I have more here? Oh, that you, there was some, here are the tasks. Sorry. So there is a seminar for us, and then I asked some examples. Cycle, click. So what's on the tree width of a click on n nodes? So how many pulleys do we need?
Yeah,
What
plus
do-
one.
What do you
And-
need for what?
That's
How we
more
have a
pulleys
click?
than nodes. Of course we will. Yeah.
Have a click on n nodes.
So yes, n.
And pulleys, yeah, of course. Can we do better?
I don't think so.
n-1.
Yeah.
And
You're
-1
right.
definitely is.
No, n-1 you can't.
Yeah,
No, you can.
no, because you will always
Oh.
go to the empty
Okay,
spot.
yeah.
So we need n pulleys, and the tree width is n-1. Okay. Complete bipartite. Oh, complete bipartite graph.
Yeah, and -1. So in this question, the tree width is actually n, with the grid.
Yeah. Indeed. Yeah.
Tree width is n. Okay.
Okay.
So in a simple path, when
The
you
tree
can,
width is 0.
yeah, the tree width is 0 then, by this definition, because
We need one police guy.
one police guy
-1 is
can
0.
catch. Oh no, one police guy can't catch.
Why can't-
Because he goes up.
Yeah.
We need two police
Ah.
guys, but then
You
we
can't catch
subtract
anyone
one
with
for
one
the
police.
tree width. Yeah.
one police guy
Okay.
is useless.
Тебе нужны эти, как это называется?
And then bipartite graph, so fully connected.
Ну,
So
кто
we have,
бэнгер, эти, что?
Yeah.
so we have n
Знаешь, чтобы
nodes.
составить водоклон, нужно два человека,
А,
которые...
понятые.
Да, мне нужны понятые. Он один не сможет.
So we have n nodes on one side, n nodes on the other side, and they're all connected. It's fully connected bipartite graph. So what will be the tree width?
N+1.
N+1, yeah, and n+1 police is needed, or
N node-
even
n nodes-
n+1.
N
yeah.
nodes on one side,
Yeah.
n nodes on the other side. We cover all the nodes on the other side, and then plug, and then we catch the. So the tree width is actually n again.
Yeah, exactly.
That's right.
Voila. And now the solution. How do we solve tree colorability problem here? And once you understand this definition, it's all easy. So let's start with tree colorability. So the claim is so input is just a graph. The parameter is a tree width. And the question, assign a color, so given three colors, assign one of three colors to every node, and each edge should connect nodes of different color. You already know this. Tree width is W. Oops. Question. Okay, I don't need to write it, okay? You've seen this before, colorability problem. You remember?
Yeah.
Yeah, you remember. But
3 ACT? No, it's not 3 ACT. It's 3 COL. It
Yeah.
reduces to 3 ACT.
so
Understood.
yeah, is this colorable in three colors? And the answer is yes. Let's use RGB for colors. So R, G, here we use B. No. Yeah.
Yeah. No, it's,
So
it's
it's tree colorable. Every edge connects two nodes with different colors. Okay. And so the runtime is 3 to the power 3 with times poly n.
What is W?
W is a 3 with.
Okay.
So that's our parameter. And so it's FPT because the parameter doesn't influence the power this in which the size of the problem appears. Okay, and so now it's dynamic programming. So how? So we get a tree with tree decomposition here in our problem. So it's FPT to calculate exact tree decomposition. So remember, I said 2 to the power order W3 poly n.
We get this decomposition.
Yeah,
right?
so we get this decomposition,
We have,
and then we do dynamic programming. So here in every, we start at the leaf,
we have
pick a
defined
leaf.
we have defined it axiomatically, right? The 3 decomposition.
Yeah,
we
yeah.
just said that we need to each node to appear in that sum, and all the nodes at which all the nodes of the 3 decomposition at which a node appears to be connected, and we need also the third some third axiom.
Two assumptions. So every edge appears
Ah.
on the back, and then for each node, we get a connected subtree.
Okay. So, yes, okay.
For each node we get
A connected subtree. For example, the node C, here we have a path of length 3. The node F is here, here. Sorry, here, also a path. Yeah, but here we don't have enough branching to get the real subtree. For node B, maybe.
so each node
So
if you select only each node, only one node.
Yeah, so we
Or-
choose a node, for example, node B, and then circle all the
Yeah,
nodes
yeah.
that contain
And
B.
this will be a subtree. Yeah,
It must be connected subtree.
Mm-hmm.
And that's the last condition.
So we can
And
we can't, for example, have B here. Or can we?
because it
Yeah,
always doesn't
we can't
connect.
because there is no B at the root.
Yeah, exactly. Yeah, that would be a
Sorry.
problem. So
Okay.
imagine that here
And
was
also-
B instead of G. It's forbidden because then we need to, unless we add B here too,
Mhm.
because then it's not connected subtree.
And
So that sorry. So here we have 4 nodes, but there is no edge between these nodes, and therefore it's not allowed. So all the bags that contain a given node,
Must form a connected
Yeah.
subtree.
Mhm.
These are axioms of 3 decomposition.
yeah,
Okay. It's G. Back.
that's correct. Otherwise, if I
So okay.
And does one bug has something about what nodes are in it?
so the definition of 3 width,
Yeah,
maximum size of bag minus 1. That's why we don't want too many nodes in one bag.
Mhm. Okay.
So now we want to understand why there is an answer that runs in time 3 to the power W times poly n. Oh, by the way, for every graph with n nodes, there is always a tree with poly n bags and minimal width. So if the tree width exists, it's polynomial size.
Okay. Was the time of construction?
Yeah.
That's really
Okay,
cool.
and so we will do dynamic programming. So we will pick a leaf and then look to all the nodes in this leaf and make a set of all possible colorings of these nodes. And so the plan is for every node to write down all the sets of possible the set of possible colorings.
Mhm.
And so we start at the leaf, and then we want to write the colors of this node, so we go first to its neighbors. And so we recursively do it on these neighbors. And then we can, when we get the 2 children, we can understand what are the colorings of these nodes that are consistent with at least one coloring here and one coloring here.
These nodes and the bags, they are not connected with each other, right?
Yeah, these are not connected.
So we get like for three coloring we get 9 colorings here and 9 colorings on the right,
yeah.
and
About 27, so 3 to the 3.
well, yeah, it's
Yeah.
27, and then we want a consistent coloring with.
So we check all
on the
27
substrate.
colorings here,
Uh-huh.
and then we take the one that are consistent with the pair of colorings here. So what is happening here? So here we drop A, that's very easy. But
It's
here,
actually not 27. It's 1, 2, 3, 4, 5. It's 3 to the 5th. Right?
so we have each node can have 3 colors, and there are 3 nodes.
no, but in 2 leaves there are 5 nodes, and we get.
So here we have 27 candidate colorings. So our table will be 27. So precisely 3 to the W is the size of our table.
Mhm.
And so here we have 2 tables, and then we iterate over the all colorings here, and we check whether there is a consistent color. So we have to just check whether the colors of B appear here, and the colors of C appear, B and C appear here.
Okay. let me see.
Oh, sorry, sorry, here it's BF, we have to check, and here we have to look at BC.
Mhm.
There is a constraint on the color, but you get it, right? Just check all color, brute force, and if there is one consistent, and so you do it for all the 3, it's finished.
Can you explain again?
Okay, so we pick a leaf.
Yes.
So the plan is to write for every node a coloring that's consistent with all the children.
Mm-hmm. Mm-hmm.
So with all its children, sorry. But then recursively, its children, we will get all the colorings that are consistent with its children. So we pick a leaf in the bottom, write all the colorings, and then we look to the parent. So we check for the other child. We do it recursively.
Mm-hmm.
Then, after we get the list of these 2, well, here it's, of course, we can, in general, maybe some more recursions are needed for this node. And then you write down the coloring here. And then you want to go up, so you do it for this node. And then you go here. And when you covered all the nodes, you're finished. If this is the empty set, no colorings, the answer is no 3 coloring. No K coloring, then okay, yeah.
Okay.
Then you can write that there is like 3 to the 5th possible combinations for this triangle. Like we get 27.
No,
colorings here, and then
once we drop a node, we drop it forever. So why can we drop it forever? For example, when we go from here to here, we drop node E. We never need to think again about color E. So when we go up, we might lose a node. And then we are done with this node. Why is it true?
Because we can always select.
So there are only 2 rules in tree-code decomposition.
Because we can color the subtree, we
Yeah.
can forget about it.
Yeah, when we forget about it, we will never go up and again need to deal with it.
Mhm.
Because we are in a tree and the nodes with a given color is,
Okay.
so that's why we get this runtime times polynomial.
I have a question. So I understand how it works, but does it always give us an answer if the answer exists?
So it, yes,
Yeah. Okay.
because we can read it off, like we can pick a color here and then we can, okay, not directly, but
No,
with
I
a
mean
bit
that
of extra work.
If a graph is 3 colorable, then this algorithm will always work. Yeah.
Yeah, you will always find it, and if it's not colorable, it will always say, find a problem somewhere.
It seems to be just a brute force, but more clever.
Yeah.
clever brute force.
Yeah.
So with this algorithm, we also can calculate the count of all suitable combinations
Yeah, exactly.
Mm-hmm.
with dynamic programming.
Yeah.
Mm-hmm.
So indeed, so we can get at the root, we get some number, and then we can go back like we do in dynamic programming. You also always get the count.
You can count any function.
Yeah, but yeah, you need extra word because you need to multiply here, when there are two options for f and two options for g, then you need to so the no drinking while programming. Yeah. Yeah.
No programming while not drinking.
So this is okay, and vertex cover you can do by yourself. It's actually an exercise if you want to do it. So to show that vertex cover is FPT with with if the tree width is a parameter.
Vertex cover is
Yeah. So how will you change the algorithm to solve vertex cover?
we
problem?
built this exact tree, right?
Yeah, so we have such a tree, we build it again, and then dynamic programming.
Mm.
I mean, we return sets of that satisfy each node. So here we return three sets: B, E, F. Here ABC. Then we somehow merge it.
If we can always select.
Maybe we'll try.
Wait a second. We either include in a simple vertex cover for a simple tree. We look at an edge on the bottom, right? Yes, and we either include no we can we either include both children or the root, but we don't ever never do this. We just include the.
Yeah, so for every node we make a table of all subsets that are indeed the vertex cover. So we just need to make sure that there is no edge between, I mean that always one node for each edge among these nodes. We need to check that every edge among these nodes is covered. So basically we make a list of all vertex covers of this subgraph given on the nodes.
And is this subgraph always fully connected, like ABC?
Yes.
Okay, and according to the definition, it's not needed, but it would be strange if you. No, it's not strange to add disconnected. For example, in a cycle. So what will be the tree for a cycle? Oh, good question. I didn't think about it myself. Yeah, it's not an easy question. Sorry. That is.
Can you explain again how do we build this tree like this graph?
Well, I didn't explain it because it's a complex algorithm. So when I asked what is it for a cycle, like once I did it, so we have 3 nodes in a cycle, and I think that you go on both sides of this. So the tree will be a path, but we can use 3 nodes each time. And so when we built the cycle, I once did it. So what will we take? So we will take these 3 nodes, and then we will have these 3 nodes, and I assume then we will take these 3 nodes. My picture, is it clear, or I should draw a large tree? Let's delete this.
This is clear, but I don't understand why we pick these nodes. We defined this structure axiomatically. We just asked for these 2 conditions to be satisfied, and we don't know how to construct this at all. We just say, okay, every picture that satisfies these 2 conditions is a tree decomposition, and we don't know how to construct it. So it's
Not I understand.
We can.
Yeah, let's do an example for the.
What properties even the bags have?
Every edge is in the bag.
Every
Ah,
edge in
Yeah.
in the bag.
Every edge is in some bag. So here is the example for this graph. So EF, we see here EF.
So every edge is in some bag,
When,
but
when we write the bag, does it mean that B, E, and F are fully connected, or
no.
No.
there
So
are
they
some
even-
edges between?
Yeah,
they can
yeah.
be like not connected at all. I think.
Yeah.
Like GH, it exists, but
Yeah, it's connected. H is on the right.
Yeah.
H is the rightmost one.
I mean,
So CDF, usually they're connected in this example. CDF is a click, but EFB, EFB, so between B and F there is no
Mhm,
edge.
mhm.
And it's unavoidable if you think about the cycle.
Yeah, because
There it doesn't matter. We only should to think about the connection question in the back. So we have to know which is the solution for the back only, and then solve up to 3 for the parents. And there is no reason to think is they all connected or only one of them.
no, I just
Yeah.
asked for.
Yeah, he was curious. That's
Yeah.
why he asked. It's not.
I'm
So
not-
what will be the runtime of the vertex solution for vertex cover with 3 with W as parameter?
Okay, so okay. Can what is the choice? We choose. There we don't choose anything. Then we choose either to take this one or this one.
So the order is the same. So we start at the leaf,
Yeah.
and then we look to all possible subsets that are a valid vertex cover. So, for example, if there is an edge between A and B, all such subsets
Ah,
would
okay.
either contain A, B, or both.
Okay. Good. And now what do we do with the tree structure?
So then we build it for here. Now we want to extend it to here. So we need a table for here. We build it recursively. And then we need to build a table for here. And so we choose all the subsets that are consistent with at least one subset here. So and that
Mhm.
means we have to look at B and C for the values here. So if our table is not consistent with values for B and C here, it doesn't appear here. And same for B and F here.
Значит, so we need to solve vertex cover for each bag. It takes us, in the worst case, 3 width to the power of k, where k is the size of the vertex cover. If we apply our algorithms, we can reduce it to 2 times k.
So what is the runtime?
Of
So you can use W and N is the, let's say capital N is the size of
Uh-huh.
the tree.
I'm looking for any vertex cover of given size.
Yeah. So just the question, does there exist a vertex cover, yes or no? And you would want to answer this. And so you run this
It
algorithm.
always exists.
of
Take all the nodes.
of size k.
Yeah, of size k.
Okay, so I need another point.
Oh yeah, sorry, yeah, you need to remember. It's a bit more.
So what do we do? Let's say we're going stupid with finding the
Yeah.
vertex cover here. We just W to the power of k. That's to find the vertex cover for each bag.
Yeah.
Not k.
So
K-
now
K-
in the table we don't say yes or no, but we will say what will be safe in the table. So here is the number of nodes of the tree, and here is okay. Here is something complicated. It's not really table, but okay.
There's a
So for a given node, we do have kind of a list, a vector. So for every subset, so the length here is 2 to the power w, right? The number of subsets that could be a vertex cover. But we don't store 0 or 1 here. I didn't say it correctly. We store something else.
The number, the power of vertex cover.
So the minimal size of the vertex cover that's consistent with this assignment.
With this set.
Yeah, for this set. So for example, it maybe we are looking here, and we can say all zeros in the vertex cover. Neither B nor C nor F is in the vertex cover. But then we might do this, but it will be expensive to cover all the other edges previously. So our table, yeah. So then this value will be high in the table. But it's also good news, because when we go up, we understand that certain nodes do not need, like there is an edge DF somewhere here. So DF might already be okay. Sorry, I said, no, it's bad. It's again bad because we need to include D in the vertex cover here. So when we go up, we can only, when we look to a possible vertex cover here, if D is not in the vertex cover, then we cannot use the all empty vertex cover here, because there is a problem with the edge FD. Okay, actually we don't need to take care of this, because every edge is somewhere in a bag here by the first row. Okay, so anyway, what I wanted to say is that in this list, we just need to store what is the minimal vertex cover that's consistent with the set. So for every subset, we interpret it as a vertex cover, and we write down the minimal size of consistent vertex cover.
It is consistent with this tree structure.
Yeah, consistent with this tree structure. So for all the with consistent with an assignment. So if there is some value k prime here, then it means that for this precise assignment of the three nodes, we can find at most k. Let's say k prime nodes below the tree, k prime other nodes below the tree that are in the vertex. I mean, there are many variants to implement it. I guess you understand how to deal with it. Oh, so. Okay. But what counts is that you know the technique.
If we counter this.
Yeah. So you can, Hamiltonian path problem, you can also solve in such a way. And then the table will contain which nodes are connected. It's okay. It's not so obvious to understand it, but just all problems in NP that they almost a lot of problems in NP that you can use this technique. So the delivery guide problem. I don't know if it's solved in practice for delivery guide. So there is a package or a set of packages, and then you have to solve the traveling salesman problem, because you want your guy to go around, deliver all the packages in minimal length of route. So it's an important optimization problem. And in principle, you could use this too, because it's essentially Hamiltonian path problem. Okay, that's very cool. Whoa, we did quite some exercises already. So, do you have energy left? Because there are some,
Not much.
like 15.3 we already did, and there is an exercise on color coding. And the new exercises we cannot do because it's about these two things. So there is just one exercise left, and then we covered everything.
Which one?
15.4. But you need to remember about color coding from last lecture. So let me quickly recall what is color coding. It's probabilistic algorithm. It's your weak spot. Okay, let's skip it. You did good. So
No, I just imagine it must be complicated.
no, it's very easy.
Very easy.
No, but I need to repeat from last lecture, and I know you're not so good yet with probabilities.
Yeah.
So let's skip it
So-
and let's finish the course now.
Okay,
Yeah.
let's do it. Let Kostya solve it himself. At home.
You want to solve it.
What?
15.4.
No, I'm even worse in
Yeah.
probabilities.
Yeah.
So yeah.
I can say that I have read the definition very carefully in the book. Not one considers what is probability. Random algorithm. Okay. Thank you very much.
Yeah, thank you. I'm very impressed to see 5 people in optional lecture. It's very good. So
Oh, good. Because
It's-
really,
It's more than it usually was on the main course.
yeah, it's twice as many students. And few.
Yeah, because we're in software engineering, like, guys do not attend the university that much. on higher
Most
courses.
guys are working, yeah,
Yes.
and then it's difficult. I mean, it's painful to go to the lectures in the evening after a full day of work, and then you have deadlines anyway, so there is no choice.
Yes.
Yeah, I can imagine that. It's quite impressive that you can combine two things.
Let me